I'll be talking to you about a recent publication with Soonwon Choi and Professor Mikhail Lukin in Nature Physics. So as an outline of my talk, we've already heard a lot about machine learning, but I'll first discuss our introduction and motivations for this specific problem. We'll discuss the classical and quantum convolutional neural network architecture. I'll discuss the particular applications that we look at before conclusions. So let's begin with our motivations. So we all know here that machine learning is this very nice method to interpret and process large amounts of data. It can be used to solve highly complex problems, and it's been used successfully in, say, self-driving cars, genomics, and image recognition. We know that in quantum physics, the presence of many body interactions give rise to extremely large complexity due to the exponential size of the Hilbert space. The problems, for instance, in quantum chemistry and condensed matter physics are typically very hard. Now, this leads us to believe that the combination of machine learning and quantum many-body physics is an exciting direction. And in particular, the development of these near-term quantum computers and quantum simulators motivates us to consider a particular combination of these two fields. Namely, we would like to use quantum computers for machine learning tasks. And in particular, these machine learning tasks can then be applied to solve important problems in quantum many-body physics and also potentially quantum simulation and quantum information. While there have been works along these directions, there were still various open questions that we were looking to answer, namely, first, why and how quantum machine learning works. What are the concrete models suitable for near-term implementation? And are there relationships between these models and what we already know in quantum many-body physics and quantum information theory? And the goal of our work will be to answer some of these questions together. So let me begin by talking about the classical and quantum CNN architecture that our work is based on. So classical convolutional neural networks are these structured neural network comprising multiple layers of image processing. In this simplified example, your input image is a cat. It goes through multiple layers of image processing here before it gets classified. The most important kinds of layers that we'll be considering are the convolution, pooling, and fully connected layers. And let me tell you what these layers do. In the convolution layer, you can think about this as performing essentially a dot product between a small portion, local portion of your input image and a small weight matrix, which is given by these W entries here. And so one element of this array here is computed as in this linear operation based on a small local subset of the pixels in the input. Now, the important part of this convolution layer is that the same formula is then used to compute each subsequent element of the array, except just switching the input pixels. So particular to compute this second element here, the gray element, you would use the same formula except switch the input elements that you're using to this gray box. In this way, only a small number of parameters are needed to characterize this one layer because you're doing this in a translation way across the input image. Of course, between successive convolutional layers, you can switch up these weight matrices, but within one, they're all the same weights. Now, the next important kind of layer to consider is what is known as the pooling layer. Now, the idea here is that you have a large array of pixels that comprise your input image, but in the end, you want to have a classification which might just be a few bits. So you need to perform substantial system size reduction for this. And classically, this is done using the pooling layer where, for instance, you can take the maximum of a 2x2 grid, and then that would perform 4-to-1 reduction, as shown here. Now, finally, once you can interleave your convolution and pooling layers with each other. When the system size is small enough, we can have a fully connected layer where essentially the output classification depends on everything in the previous layer. So then the parameters to be trained when you're learning a convolutional neural network would then be like these weights in the convolution layer, for instance, and also the weights in like the fully connected layer. So that's the classical network structure. And let me now introduce the model for quantum CNN. So we would like to have the same types of layers, but we have a quantum circuit model now with this similar structure. So in this case, our input state will be a generic pure or mixed state. And this could be a classical or quantum state. I'm illustrating this here in the case of a single spatial dimension. The qubits are in a 1D array. But more generally, this could be easily generalized to 2 or higher dimensions. The convolution layers are now going to be translationally invariant quasi-local unitaries. So what this means is that you take one unitary acting on a small number of qubits, for instance, this 2-qubit unitary here, you apply it in the same fashion to all the nearest neighbor pairs of qubits. Now, the pooling layer, we also want to reduce the system size here. What we can do is we will measure a fraction of the qubits. These symbols here are the measurement operations, and we will apply unitaries to the remaining qubits depending on the outcome of the measurement. So, for instance, your measurement outcome could yield plus or minus 1. If you get plus 1, you do a particular rotation on the neighboring qubit. But if you get minus 1, you can do a different rotation. Again, the convolution and pooling layers can be interleaved and repeated until you get to a small enough number of qubits that you perform a fully connected operation, which is, in general, a non-local measurement. And so the weights to be learned in the quantum CNN would just be the parameters to each of these unitaries. And one important property to note here is that if you have an input state consisting of n qubits, then this circuit can be parameterized with just order of log n parameters. By contrast, if you wanted to do a generic n-qubit unitary, that would require exponentially many parameters in n to specify. So this dramatic reduction allows for efficient implementation and training of our algorithm. So now I've presented our circuit model, and I've said that this has a dramatic reduction in the number of parameters. But now I need to convince you that with this reduction, we can still do useful things. And so this leads us to the particular applications that we've been looking at. The first application I'll be discussing is known as quantum phase recognition. In this application, we can consider different quantum phases of matter. So classically, in physics, you know that there are different phases of matter, such as solid, liquid, or gas. But once you add these quantum mechanical effects, in general, the phase boundaries can be much more complicated. And studying these different phases of matter is actually an important problem still in condensed matter physics. So the particular problem that we'll look at for our QCNN to solve is, suppose you're given a quantum many-body system in some unknown state ρ, and we're asking whether ρ belongs to a particular quantum phase of matter p. This is analogous to image classification. You're looking at an input state, but it's an intrinsically quantum problem because the input state is encoded in qubits. It could be a quantum state in general. As an example, this problem could be important to, for instance, quantum simulation. If you're trying to prepare an interesting state which belongs to a certain class of states, this P, then you want to verify, for instance, that you prepared the right state. And if you can solve this problem efficiently on the QCNN, then you can help to verify that you prepared the state in the interesting phase of matter. Now, our claim is that QCNN can be very efficient in performing this quantum phase recognition task. In particular, the final measurement of the QCNN will have expectation value very close to 1 if your input state belongs to the phase, and close to 0 if it does not belong to the phase. So as a particular example to demonstrate the success of QCNN at this problem, we examined this model known as the ZXZ model. Our input states are ground states of a family of Hamiltonians shown here. In this formula, the Z and X symbols are the Pauli Z and X matrices. We assume that we have an input chain of spins, which are on a one-dimensional array. This model here defines a particular quantum phase of matter, which is a symmetry-protected topological phase protected by Z2 cross Z2 symmetry. The details of what an SPT phase is aren't really important, but the key property here is that this phase of matter can't be detected by a local order parameter. So what this means is that you can't, for instance, just measure the local magnetization of your spins to determine whether you're in this phase. For the people who might have heard of it, this is also the similar phase transition as the S equals 1 Haldane chain. So in our demonstrations, we first looked at the phase diagram for this model using traditional methods where, because these are second-order phase transitions, we examined the second derivative of the energy density and identified the peaks in this second derivative to get the phase boundaries. These are shown in the red and blue diamonds on this diagram. And then what we did was we designed a QCNN circuit to recognize this phase. And we did the simulation of the QCNN circuit. And you can see that the color plot shows the expectation value of the final measurement. And it reproduces this phase diagram very accurately. So in this parameter regime, you have 3 relevant phases of matter. And we're trying to recognize the SPT phase. So the output is almost 1 when you're in this SPT phase and 0 otherwise. This right plot here is just a one-dimensional cut of this diagram. So we're looking at sweeping one of the parameters of the Hamiltonian and looking at the expectation value here. And the different colors signify increasing the depth of our network. And with higher depth, you can get sharper and sharper classifications near the phase boundary. Now, this sharp classification is nice. We want to translate this into a direct quantitative advantage over traditional methods. So I mentioned earlier that these SPT phases cannot be detected by a local order parameter. There do exist these traditional methods of looking at string order parameters, which are, in general, operators supported on a large number of your input spins. So they can be typically hard to measure. But the idea is that if you have one of these string order parameters S, and it takes values plus or minus 1 typically, if the expectation value is strictly greater than 0, then the input state belongs to the phase. But if it's exactly equal to 0, then it doesn't belong to the phase. So this theoretically is a very nice concept to classify different input states. But there actually experimentally can be quite challenging to use this technique. In particular, this is because near the phase boundaries, where the classification is hard, this operator typically has expectation value which rapidly approaches 0. To get a more concrete picture of why this is hard to use, you can think about an experiment where I give you 2 coins. One is fair, 50-50, but the other one is slightly biased. It's 51% heads and 49% tails. And now you're like, I don't tell you which one is which, and your task is to find the biased coin. Now, you can imagine that this would take you many tries to figure out which one is which, because they're so close in the probability distribution. And that's exactly what it's like to use one of these string order parameters when you have an input state near the phase boundary. But on the other hand, the QCNN is much sharper near the phase boundary. And so it should be much better to use QCNN. And we can characterize this advantage using what's known as the sample complexity. Here, we look at the number of repetitions to determine that an input state belongs to the SPT phase with 95% confidence. The blue curves show the performance of QCNN. The red curves show these traditional methods. And you can see that QCNN clearly significantly outperforms the string order parameters. So in addition to this, we also have a theoretical understanding for the success of the QCNN model. while traditionally a lot of quantum machine learning approaches rely purely on numerical demonstrations, here we actually connect the QCNN to two important concepts in quantum information theory. The first of this is the multi-scale entanglement renormalization ansatz, which is an efficient method to represent or to generate these interesting entangled states. So in particular, you can start from qubits in a known deterministic state, for instance, the 0 state, and then you can apply successive layers to these qubits. So the orange boxes here would consist of injecting a new qubit in the, for instance, 0 state, and then applying an entangling unitary between this qubit and an existing qubit. These are known as isometry layers. The blue squares here consist of just two, for instance, 2-qubit entangling operations between two of the neighboring qubits. And after many successive layers, you can generate interesting entangled states psi. You can see that this entanglement renormalization is very similar in structure to our QCNN model. However, there's an important difference, namely that QCNN runs in the reverse direction. So instead of generating these states psi, what we're doing is we're trying to take as input a state psi and classify it. And in particular, the pooling layers, instead of injecting new qubits, we're measuring one of the qubits and performing a rotation on the remaining qubit depending on the measurement outcome. Now, this measurement, of course, might not always yield the 0 state. It could yield a different state, and in that case, our QCNN has this additional degree of freedom corresponding to what we're doing in that case. So we can actually interpret that additional degree of freedom as quantum error correction. So in particular, if you have any state generated by this MERA, you can always represent it by a QCNN, which is the inverse of this MERA. But we also, for phase recognition, want to recognize states that are very close to this input state psi, but maybe differ from it by a little bit. So they're still in the same phase of matter as psi, but they just differ by small perturbations. And the idea is that QCNN treats those small perturbations as errors, and the quantum error correction part of QCNN will correct for those errors and recognize that the two states are in the same input phase. So to explicitly demonstrate the training capabilities, we looked at a simulation with a smaller number of spins, here 15 spins, and we initialized all the unitaries to random values and performed gradient descent. We trained along a line where the input model was solvable. So this is a set of points on the diagram where you can analytically determine which phase of matter an input state belongs in. And what we observed was that even though we trained only on this 1D solvable set, these gray points here, the model was actually remarkably able to reproduce the 2D phase diagram. And so this demonstrates, for instance, that the QCNN structure is very good at avoiding problems in machine learning, such as overfitting. Now, so that concludes my discussion of the first application. The second application that I'll be looking at is the optimization of quantum error correction. So we've already heard a lot about the necessity of error correction in this conference. We know that quantum computing can be powerful for a variety of important tasks, but due to the presence of qubit and gate errors, in general, you need to perform error correction for scalable computations. Depending on your hardware, you might need to do more or less of this error correction, but it is still necessary in general. And this is just a figure I took from Daniel Gottesman's slides. But to enter the kingdom of quantum computation, you need to pass through the land of quantum error correction. So in general purpose quantum error correction, the main observation that people use is that single qubit errors can be generated by two different kinds of errors, namely the Pauli X and Pauli Z errors. So if you represent a qubit on the block sphere, then the X error corresponds to this bit flip error, and the Z error corresponds to the phase flip error shown here. And by correcting both of these errors, because all single qubit errors are generated by these, you can correct for all of the single qubit errors. And that's how quantum error correction usually works. As a quick example, we can first motivate the quantum error correction using like the classical repetition codes, where a single bit can be encoded into, for instance, 3 copies of that bit, and you do majority vote to determine, say, that this third bit is flipped. Now, quantum error correction is actually more complicated due to various reasons. For instance, with the no cloning theorem, you know that you can't just take an arbitrary qubit and copy it 3 times. You also don't want to collapse the wave function whenever you detect for errors. And as I mentioned, you need to correct for 2 kinds of errors, both X and Z. The nice solution that people have come up with is to measure what's known as stabilizers, and these can be thought of as correlation functions. So for instance, in Shor's 9-qubit code, you're looking for these different stabilizer operators here. And as an example, like if you these Z errors are like doing this repetition code, the majority voting for the bit flip errors, and if Z1, Z2 is measured to be +1, while this Z2, Z3 is -1, then you determine that the qubit 3 has X error. This is exactly analogous to this diagram here. This all works very nicely. However, the challenge is that real experiments might not just have single qubit X and Z errors. In particular, you might have correlated errors, which in which 2 neighboring spins flip at the same time, for instance. And these single qubit codes would not be able to correct for these correlated errors. So the problem that we look to solve using our QCNN is, suppose you're given a realistic but unknown error model. Now we want to find a resource-efficient quantum error correction code to protect against these errors. To do this, we notice that the QCNN structure closely resembles nested quantum error correction. And we use this fact to simultaneously optimize both the encoding and the decoding procedure for the error correction. So we start out with a single logical qubit here. We applied the inverse of the QCNN procedure to encode this logical qubit into physical qubits, into many physical qubits. These physical qubits could undergo some error channels. And in the end, we use the QCNN circuit to decode these physical qubits into a logical state. In general, this might differ from your initial state by a little bit, but we will be optimizing for the overlap between these states and to get the best possible error correction code. So the particular circuit structure we used looks like this. And indeed, we found that when there is correlated error, the QCNN code can significantly outperform known codes such as the Shor code. This is even in the presence of just like a very small fraction of correlated errors. So this brings me now to my conclusions. Today, we've discussed a concrete circuit model for near-term quantum machine learning, namely the QCNN. I've discussed 2 important applications of this model. The first was for quantum phase recognition, second for optimizing quantum error correction codes. Now, thank you very much for attending, and here's the link to the manuscript.
We have time for 1 or 2 quick questions. Yes.
So, I understand that you showed an example, and what you did was, in your example, you did quantum phase recognition. You applied the quantum network to that. Can you take the same network and apply it to a real-world image, like a cat's image, and try to get an answer out of it, cat or dog?
Right. So we, of course, haven't tried that, but I believe that the model should work for this purpose. Here, the distinction from certain like these quantum machine learning algorithms designed to do image recognition is that we aren't actually encoding, for instance, in a quantum RAM, just to avoid this input bottleneck. So realistically, if you think about having the number of qubits like similar to the number of pixels in your input image, it might be like a while before we get there. But I guess it would probably work. We haven't tried it on I know some people have tried like subsampled like MNIST data or something. We haven't tried that yet, but that would be interesting to consider.
One more question.
So for the quantum phase recognition, I guess I was just curious about the sensitivity to errors in the preparation of the initial state, and I guess how those propagate to the final result you get.
Right. So in our case, we didn't like explicitly try to introduce errors in the input state, but the idea is that because this QCNN structure contains this nested error correction in there, if you only have local small errors perturbing your input state, then the state should belong in the same phase, and like it should be corrected for by the error correction in the different layers.